Here's a video to describe problem, the MATLAB code that I created for a full rotation or multiple rotations of Norton problem 531. I wrote the MATLAB code and I provided it, and a couple of people asked about the different features of it and what they meant. So here's the problem that problem 531 in the book, and here is the solution to it in mechanism form, and here is what it looks like when it runs. And I'm tracking this point up here is my point of interest, mostly because the original problem used that point as P1 and followed it along. It was like the point of interest. We would like to replicate with SolidWorks, if we can, a plot of velocity. So let's see if we show it. So we're looking for plots like this of that point. Even though it looks like a little bit of an arc, there's some interesting differences to it. I believe this other one right here might be acceleration. We'll be looking at that one as well. And it has some quirks. These aren't just sinusoids, so this is both the x and the y component. So let me go back to my MATLAB, so here's the MATLAB right here of it, and I'll hit go, and you can see that we've produced. Here's an arc, a trace of the thing, and here's also the velocity. If we were to plot those up next to each other, we would see that they're very similar. I think the SolidWorks one uses a different scale for each of the two plots, so they're not proportionally the same to each other like this one is. But we could export that into Excel and check it out. But let's take a look at what's going on in it. And I figured it would be better instead of just scrolling down through here. Although you could, I mean, that's one way that you could learn. You could go step by step by step and see what each of these things does. I'll try to describe it. I don't know if that's useful. So first thing you want to do is find out like some initial positions, and definitely figure out the lengths of all of these things. So that would be the output from the previously discussed homework for analytical synthesis. This is what the piece looks like. I've drawn the vectors out, and now here's the vector loops superimposed on top of the problem and also separated out. The main idea is the driving dyad should be a Grashof 4-bar, where it's this crank R2 is the one that's making the thing go around, just like in the real die. And then the output of that is R4, which actually overlaps with R6, and now that becomes the input, and that's just a rocker back and forth. So these are the conventions that I'm using. I'm continuing on with what was used in Norton. The only difference is that there's 2 4-bars now instead of just one. And whereas Norton does a weird thing where the ground is number 1, I decided to keep the ground number 5, and the origins of both of the vectors are here at this spot right there, which is the same spot as this guy right there. And where this is like length A, B, C, and D, which is kind of weird because this is vector 1, I went ahead and did the same thing, continuing on with E, F, G, and H. And then all of the angles are numbered with the theta 2s, theta 1, theta 2, theta 3, theta 4, and then likewise theta 5, theta 6, theta 7, theta 8, down here. And always making the angles at the base of the vectors. And for this point up here, this point of interest, I had that vector as P. I think I have labeled its length like AP or something like that right there. And then this del is the angle from horizontal. And that kind of gets added to theta 7 to be able to establish where that location is. All right, so here's some of the preliminary stuff to tell you, clear things in here. And then here are the dimensions and the starting angle for theta 1, right? Because theta 1 is now at this particular angle. It's been 0 a lot, but we have it now at negative 31.5. You can't go negative. That's just, you're going clockwise instead of counterclockwise. And then I also have all the dimensions for my rocker. And its theta 7 is, or its initial angle is 0, right? That's because the thing is up, straight up and down. I should also mention the one that we're seeing over to the side is at a non-aligned position, right? I purposely, when I drew out my vector loop, I moved the thing a little bit because when we were up here, these vectors are in line with each other and you can't quite see them right there. So I decided to move them just a little bit, enough that you could tell. So, but notably, I believe this vector right there, which is 7, that's horizontal 0. That's why that's there, yeah. All right, so we have all the initial things, so hopefully that helps you orient where you are and where you want your things to be. Then I also mentioned that, okay, so P is the length of this piece right there, and I'm calling it gamma, but I bet that's del and not gamma. So I named it the wrong thing. I talked about the initial position of the crank, and then had the input angles for, okay, so now I make a string of angles, right? So here's the initial one, which I probably could have gotten, no, I hadn't. Okay, so I hadn't put in what theta 2 is here. So here's where I decide where theta 2 belongs, the initial one. And once again, I got that from like the graphical synthesis. And so I send it through for 2 rotations. You might just want to do 1 rotation, but I kind of like the look of 2 rotations when I'm making a video. And now I got omega 2. This was going to be for 20 RPM. We might want to change that when we go to try to match some other methods of finding the velocity. And then I do the trick of making time, finding a time string by way of, let me see what I'm doing here. Yeah, take theta 2, okay, so here's a time at each angular position. Yeah, I think let me double check that I'm saying that the right way. Yes, okay, so because we want time to start like at 0, I think that'll be correct. All right, so with the driving dyad calculations start right here. So what I'm basically doing is I'm doing a position analysis just for this first 4-bar. And I establish how long I want these angles. I'm filling up with zeros, the angles, and then I'm about to populate them. And I populate them in the loop. So the original one I want to do is, so I established both of these 2. One of them is, I think, are these initial guesses? Let me see right here. Crank and coupler aligned at initial position. Oh yeah, that's true. All right, if you go back to the beginning, you would see that this guy and this guy, when we're going to say the initial condition is when they're aligned with each other, when this piece is as far left as it'll go, so that the crank has now aligned R2 and R3 together. So, but they are actually 180 degrees apart and being in line with each other. And then because it ends up being a triangle, I use law of sines to get that established. So I could go back and kind of like explain that better, maybe if it's not clear. So like when you have right here, those two are in line with each other but facing each other different directions. And so if you want to know what the angle of the blue guy is going to be, we could use law of cosines to be able to establish that. That's what I'm saying is the initial conditions. Like watching paint dry. Yeah. All right. So once we have that, driving mechanics. No, we already did that part. So here's the initial conditions, and so we established this F thing. That's what we're going to do is we're going to try to reduce the size of that. So every time we go through this loop that we just started right here, that we're using n to count through with the length. I think I had to add the +1 just to get the dimensions to work out correctly. And so our estimate is going to, so n starts at 2, but then in here, we're going to subtract 1. So we're actually going to use as our first guess this thing down here, what we got from these initial position angles, which is a good thing to do because then we're going to be pretty close. And I guess I didn't have to write out this top one right here because it's right down there. So I think that might be redundant. So I'm going to try getting rid of that and see if it works. I don't think it hurt anything. Now I set up what is essentially my Freudenstein equations right here. These are the things I'm trying to solve. And I'm going to numerically try to solve them by taking, first off, I believe this is, I want to say it's the Wronskian. I think I said that might be the wrong name for it. It's when we take the partial derivative of each of the things, like the slope of them with respect to the other parameters, and we use that, and along with this B matrix right here, we use that to try to solve. We get an X position onto the thing, and we just keep doing it over and over again, and changing the results, right? Changing the estimate, and then repopulating it here with the new estimate, the new estimated angle, and then repopulating F, and then just keep going back and forth until it narrows down on these unknown theta 3 and theta 4. And when you're done, we establish for this particular data point, this time point right here, we populate and we fill in the blank of the zeros that were right there for that time step. And then we do that until we have the entire time of what the angle. So for every crank angle input of theta 2, we have now we have known theta 3s and theta 4s. So we've essentially done a position analysis for all the different time steps. And then I get rid of the first angle. I've always wondered why I do that. I got to get the dimensions the correct. So that's the one I decide. A lot of times it'll be the end one that I'll get rid of. So I'm a little curious why I did this, but generally that's what the reason for. Where it might be that positions 1 and 2 ended up being the same angle. So I didn't need two of the same angles in a row. So I clipped off the first one. And then you take that information that we had for the rocker, and now we're going to do the same thing, but this time we're going to do it for this for this 4 bar, and the input is of theta 6 is going to equal theta 4, right? So we say that right there, theta 6 is equal to theta 4, theta 7 was all the zeros, and theta 8, right? So theta 7 is the angle for this vector, and theta 8 is for this vector right here. And then we get some initial guesses right in there. I guess where are we getting theta 7i from, though? That's interesting. Where did theta 7i come from? I must have set it in somewhere. Theta 7i. Oh, there it is right there. Okay, so I said right from the top, these are things that came in for us that we got from the synthesis results. Also, the theta 7, we just happened to know it was horizontal. All right. So that's the initial guess. And of course, the initial guess is going to, because we picked the correct angle, it's not much of a guess. So there you go. We have those angles, and then we set up, and I think I'm doing this redundantly. I don't think I need to write that thing twice. So I'm not sure why I did that. But I do set up the length of this for loop. And we have this, here's our criterion, and we figure out what all the angles are going to be for each of these time steps. And we just go through it again and again. And now we have all the angles. We have 4 pieces of information that are tied, which are theta 3, theta 4, and theta 7, and theta 8. And we have those for every time step that correlates, that's related to a theta 2, which is the main input. And so now we can just see what we got, right? We could track and see what our position is going to be. So I take, looks what I do is I take D, yeah, and I just plot where they're located, right? So D, and I have my theta 1 and D theta. Okay, so here's the base of the thing. What I've done, I don't know why it's not on here, is I've taken this spot right here. Let me see if I let me come back out of this. How come you won't let me out? And okay. Oh, okay, that's because of this. All right, so let me move this guy over a little bit right there. And I don't know if this will scale because it's a group. And it probably won't. It's probably going to mess everything up. All right, so let's go back to this. All right. All right, so I want to find this spot right here. And I'm going to call that CC for some reason. What I do is, because I decided, I guess this is the origin for my thing, and maybe it would have been better if I made my origin down below. Maybe I should try that again and write that out that way. But I go down D, cosine and sine of theta 1, right? So this is length D. So that'll get me this position with respect to right here. And then I go E, which I believe is A, B, C, D, E is it E? That doesn't sound right. E, F, no, wait a minute. A, B, C, D, E. Seems to me that this should be F. I should be writing F, not E, right there. If I went down to here, and then I came over to there. So I should double check my own thing right there. Because this is theta 6, and that should be, if I recall correctly, the length. Oh, no, that is E, right? No, yeah, that's right, because F, A, B, C, D, E, F. No, I'm wrong. I might have got those switched. Okay. So I think that should be F right there, because we made it down to there. And then we're going to come up with theta 6, and we're going to get up to here. And then we're going to add to P times theta 7 plus gamma right there, right? So if that makes any sense to you, I can attempt to use a highlighter right here. You know, where's the highlighter? Okay, so we're going to come down here. We're going to come up to there, and we're going to go over to there. And that's going to be from there to there, there to there, and there to there, from the X, and then the same thing for the Y. And the signs will take care of themselves, and hopefully this thing will come out to the right place. But I need to like double check my own code because I'd never noticed the whole E thing. So let me take a look. What do we decide? All right, so this we have A, B, C, D, and A, B, C, D, right? Because those got from the positions of the thing. We did it twice, so I hadn't named it yet. So when we get down to here, see, I got the right answer, but I didn't stick with my convention. I should have. I made the ground H. No, well, no, that's correct, right? Because A, no, that's right, yeah. Because A, for some stupid reason, is the crank. So if that's the crank, then it makes sense that this right here would be the next letter after the ground, right? Because the ground is D here, and then the ground is H over here, which would be this guy right there, which just is confusing, but that's what Norton did, so I stuck with it. Oh, I highlighted the wrong thing right there just now, but don't worry too much about it. All right. So other things that are remaining here are really just graphical things to help check your model, right? So that's this is following the point, and I plot the thing out so you can see it. And I call this points for plotting because that amused me. And I'm not sure what the n equals 1 does, but so let's try to figure that out. All right, so I found a bunch of these different vectors. Oh, I know. This might be set up so I can make the thing animated. That's what I'm trying to do. So I never did it, but you could do it right here. But I just used angle 1 for all of these things right there, right? So if you wanted to later on set this up and run it for like try to make an animation, I think I failed at that, and I never got around to fixing it again. So here I just want to, because I couldn't get quivers to work in the way I wanted to in a repeated way. But the quivers I felt like really helped to try to visualize what the location of each of these things were. Um, I don't remember exactly the meaning. I don't think the fourth thing mean. I'm not sure what the fifth part of each of these things is. They just have it as 0. But I ran across the quiver command and felt like it was a pretty good one to try to demonstrate the position with MATLAB. There's many other ways that you could use the data we have. But you can see from these right here, we're just basically taking X and Y and finding an orientation of them. Like each of these quivers is a vector that floats around, but or each of these positions is a relative position or a component of a vector that's just floating around. But then when we take these quivers, we can build off of them. So we could start off at an origin, and then here's the end point, right? And the same thing in the, yeah, because we're starting from right here, right? So one goes up and one goes down, and then you could build off the same thing with the R3. It starts off with end of R2, it goes off of that way. See if the R4 starts off at the end of R1 and right here, and then goes up to where its R4 is going to be, and so on until it plots. I'm not sure why we have this plot twice here. It's that's interesting. I don't know. It could just be. I could be losing my mind. I think. Oh, I know why. It's because I wanted to include the little plot symbol on there. That's why it's on there twice. Okay. And then lastly, I do a velocity analysis. I take at the tip. I take this command right there, and this just describes taking a numerical derivative of the thing with respect to time. It's the delta x over delta t basically, and then I plot it. So that's the big idea behind this, and it's not terribly difficult once you start to mess around with it. The difficult aspect that you'll have is trying to get, if yours is upside down or backwards or whatever. I think you just have to monkey with it. You can use this quiver thing to double check that you have the correct orientation. And although I do have it set up so that you could keep using different angles right here, right? So if you set up your angle to, I'm not sure how many there are of these things. Let's see, we said n up. So how big is n? N is only equal to 1. Oh no, that doesn't make sense. Okay. What is the dimension? We have 721. So if you were to go, I don't know, 150 or something along those lines right there, and then plot just this, I think. Yeah, so you could see where the location was of your plot and see if it made sense, right, compared to perhaps one over here where you'd of course this one has no, oh, no, it'll let me do it. No, what happened to this guy? I thought I got rid of him. Well, let me do it. No, won't let me do it. Maybe we need to suppress you too. Yeah, it's something like all along right over there is what we're seeing in right here, right there, right. So you can kind of see how those are oriented, and of course that point is that point right there. So hopefully this will be useful to somebody in some way. But I'm not saving any of these things. Don't save. No. And shutting down. All right, so let's go undo. Undo. Any other undos? No, that's the only thing I did. All right, well, good night.